Image classification using convolutional neural networks. In this agenda, we are going to see introduction to image classification, deep learning, in that we are going to see convolutional neural networks, architecture, and some of the successful CNN architecture, and one of the experiment in Google Colab, and at last key takeaway. Image classification is the task of taking an input image and taking as a output with a class of probability where it describes the image belongs to what type. So here you can see there are group of images where some are nature images, some are gadgets, some are vehicles, some are aeroplanes, some are ships, so many things. So how to recognize and classify that images with the help of neural networks. So this is able to quickly recognize the patterns. So this is what we see as a human being. This is a cat image, and if I take a small part of that cat image, it when we import into the computer vision takes with a type of pixels. So this is a pixel values of that small part of the image of the cat. So this is what computers see. Let's take one example of the dataset from the internet, which is a CIFAR10 dataset, which consists of 60,000 of images by the size 32 by 32 color images, and with 6,000 images in that per classes, like per classes in the sense 10 particular classes like airplane, automobile, bird, cat, so on. So like that, we have a 50,000 training images and 10,000 test images in that. So we can take a demo on this later. So let's understand what is the color images. Usually the color image like this with the fruits and vegetables, it is in the form of color red, green and blue, like this red, green and blue. And usually we'll convert into first grayscale image like this. So if we take a one image which is of in the form of blue, green, red with a m number of rows and n number of columns. In that, if you take a small one pixel as a small box in that, so this is how we can visualize it. So handcraft features is important in image classification. We can consider text features as histogram based, entropy, heraldic features, gray level run length matrix, local binary patterns, many more. And morphological features like hues movements, shape features, granulometry, and bending energy, roundness ratio. So we'll see this image processing or image classification using deep learning, which is where we have a subset of machine learning. So this objective of moving machine learning to the closer of one of the original goal, artificial intelligence. So we have many more neural networks in that important is convolutional neural networks used for image classification. So let's see its architecture first. It has architecture with the different layers starting with a convolutional layer, pooling layer and fully connected layers. If we have an input, then we have to feed into the convolutional layers which has a feature map. Feature map can be calculated by using the kernel, which is nothing but a filter, which has to be stride on each of the input matrix to get the feature map. That we'll see later. So how it is architecture has been built, you can see the number of convolutional layers 1 2 3 4 like that, which is making to build a feature map, and then it is moving to the pooling layers where it is making the subsampling for resizing the image, and then again number of convolutional layers, then resampling. So like that it goes till we take the fully connected layers at the end, and then classify using the softmax as an output. So it has equation as I into k. I is input matrix and k is a kernel. So it is taking the summations of both k and r with respect to I and j rows and columns. So if we imagine this input has an image of this value in the form of matrix, it is multiplied by filter which we are taking as a kernel. When we make a dot product of these two, we are getting the feature map of that image, and it is convoluted as a convolved feature. Okay, so this is for activation map to make as a feature map of each small part of the image. We can see with one of the example with the rat as a original image, and we'll take one small part on that image, this part as a curve one. So this detector will make the pixels of that filter first, and that filter will be multiplied with the pixel representation of the receptive field. So in the receptive field, when you make the multiplication and summation, you are getting the particular large image, and that is detecting a spatial features with a large one, and you can identify easily and clearly. Similarly, we have taken one more thing, same thing, taking the filter and multiplying, we are getting the multiplication and summation. Convolutional layout. Okay, here. Convolutional operators, which is mainly used to produce the feature maps, as I said. And for the particular input images, we can have a different filters like this. So if I take this filter, just identity, and if you take different features for edge detections, it is taking like this edges of that image. And if you want to make a sharpen, you can take a different filter. If you want to have a box blur, you can take a different filter, and same like a Gaussian blur. Let's take one input of this type of image and how we can make in the form of convolution of that input matrix with a kernel. So we'll take one three channels of red, green, blue of that input image, and we'll apply to the kernel of this for kernel channel 1, 2, 3. Then we'll take the dot product of that, and then at last make the summation. We are getting the convolved output like this. So this is about a convolutional operator. So in this convolutional layer, it learns the values of these filters on its own during training process. Although we still need to specify parameters such as number of filter, filter size, padding, and stride before the training process. So this looks like this. So if this is a particular images, how we can take in the stride of that with the kernels. So this is through that we need all these things: filters, filter size, and padding, and striding on each things of the images. Along with the convolutional layer, we have to apply the activation layer. Here we are applying rectified linear unit. So this is used after every convolutional operation, and it has the method max of 0 comma input. It's basically an element wise operation and replaces all negative pixel values in the feature map by 0. And the purpose of ReLo is to introduce non-linearity to the network. Through the activation layer, here you can see input feature map. When you applied reload, it shows like this type of rectified feature map. Here black means negative and white means positive values. Only non-negative values, if you are seeing here, that is with a white color. So even we have other nonlinear function like tan h, sigmoid, that can be used instead of ReLU, but ReLU has found to perform better in most situations. Then after the convolution layer in the architecture, we have a next layer which is pooling layer. Pooling layer downsamples the volume specially independently in each depth slice of the input. So this if we can take a convolutional layer convolved output that can be going to the pool of that. It is downsampling, resizing it, and then it is making downsampling in this way 224 by 224 downsampling into 112 by 112. So single depth slice is max pooling into 2 by 2 filters, means 2 by 2 matrix value by striding 2. So the most common downsampling operation is max pooling. It is to rise the max pooling, and here you can see the stride of 2. As I said, in the architecture, we have a convolutional layer, then pooling layer, then at last comes fully connected layer. In the fully connected layers, neurons in a fully connected layer have full connections to all the activation in the previous layers. So you can see here in this diagram, the input is first move into the convolutional along with the ReLU activation function, then pooling, and again convolutional plus ReLU plus pooling. Like that, we have a number of convolutional layers along with the pooling. Then at the last, we'll flatten, and then comes the fully connected layers, and at last it goes for classification with the help of softmax activation function to classify the images. Here we'll take with one example. So there is a car image. We have to detect whether it is a car or truck or airplane, like that, out of the data set. So it takes with a input, then it moves to the convolutional along with a ReLU activation function, then it goes to the pooling, and then fully connected layer. So you can see here this convolutional and ReLU into 2 means twice we have a convolutional layers and ReLU, and 3 means this is continuously doing thrice, like this: convolutional, then ReLU, again convolutional, ReLU twice, then pooling layer, then convolutional, convolutional, and then pool, and then convolutional, convolutional, pool, at last fully connected. Like that, it is going for the networks of layers to make a images classification. So in the fully connected layer, it is occupied as a car, and then it is detecting and classifying this image as a car. We have a different successful CNN architectures. So we'll take some examples. LeanNet 5, this architecture is excellent. First architecture of CNN. Input, number of convolutional 1, pool 1, convolutional 2, pool 2, then hidden, then output. So this is good for identifying the digits in the images. We have another AlexNet, which is famous for winning the ImageNet large scale visual recognition challenge. We can call it as ILSVRC in 2012. So it has a first C1 convolutional layer, 2, 3, 4, 5. Then we have a fully connected layers of like this 6, 7, 8. So this is again organized for the better visual recognition. And there's one more VGGNet, which has a clear image of this input, and it is going to the convolutional plus ReLU in wherever black boxes are shown. And then wherever red, it is showing with the pooling layers. And at last, in the blue color, it is showing fully connected. And at last, in yellow color, it is showing softmax for classification. Here we have one more AlexNet. Okay, it has only few convolutional and pooling layers, then fully connected layers, and then for this uh, VGG net 16 and 19, we have a different pooling layers and fully connected, and here also fully connected layers at last, and first pooling layers, and before pooling layers we have many more convolutional layers. You can see here wherever there is a orange color, these are convolutional layers, and wherever there's a blue, these are pooling layers, and at last fully connected layers. So as per its version and high weightage of evaluations, we have a different purposes CNN architectures. Let's see the experiment in Google Colab now. So you can have a practical implementation with a quick review. So image classification using CNN I have used with the .ipynb, which is interpreter Python notebook I'm using in Google Colab. So you can just use the code for writing the code, for making the markdown you can write a text. So I have written already code and executed. Just let me show you. First, we have to make a import of required libraries like NumPy for numerical calculation. So import NumPy as NP as a shortcut name, and import matplotlib, which is for data visualization, .pyplot for making the plot, and make the short name as PLT. Similar way, we are taking TensorFlow, which is a module for building the our neural networks. So I'm taking as a TF, TensorFlow. And tensorflow.keras, which is on top of tensorflow, we have a keras to import the layers and models. We are taking it from tensorflow.keras. Like that, can import a CIFAR 10 as I shown. CIFAR 10 has 10 data sets, particular sets from different training images and testing images. Let's import directly from this tensorflow.keras.datasets. And import to categorical, we have a tensorflow.keras.utils. From that, we have to import it. I just made it run, and after that we have to load the CIFAR 10 data set. So to that I'm taking xtrain because we want a training set, and then ytrain for the output, and xtest for testing input, and ytest for output testing. So that we are assigning to the CIFAR 10 dot load data. This is a method to load the data. And then once the loaded the data, we have to make into the normalization. To normalize the pixel values from 0 to 255 into in the range 0 and 1, we have to make x train comma x test equal to x train divided by 255 and x test divided by 255. So it's converting from 0 to 255 range into the 0 and 1 range. Then we have to convert labels to the one hot encoding. So one hot encoding make the conversion to the categorical. So first 10 this y train, then y test. So I have just made it run. So it has been downloaded like this after running. Then we have to visualize some training images with class name. So I made it as a class name with a list of airplane, automobile, bird, cat, deer, dog, frog, horse, ship and truck. I already shown you in the PPT. So first I'll make the figure with the figure size with the PLT from the matplotlib. PLT dot figure of fixed size of 10 comma 2 with the size, and in the range of 10 for I in the range we are making the subplot, and x takes I am show for showing the image, and then x label for making the label of the class names, and subtitle for showing it sample training images, and plt dot show. So it is showing some sample training images like this. It is blurred images almost, but it's okay. Still CNN recognize it. We can see at last. So this is frog, truck, deer, automobile, a bird, horse, sheep, and cat. So now is the time for building CNN model. So building the CNN model, first we'll call models.sequential because it is a sequential model. And then we'll call the convolutional block by adding the layers to the model by model.add of layers.convolutional 2D with 32 is a units and 3 by 3 is a size, and activation we are taking as a ReLU, and input shape we are taking 32 by 32 by 3. So I have already shown with the architecture. Similarly, we are writing in the Python. And then we are adding the layers of max pooling. As I know, in the one convolutional layers we have along with the ReLU and also max pooling. This is an important pooling method. And then second convolutional similar way we are taking. Next adding the layers, and again third layers we are making the same convolutional, and at last we flatten it, and then we are adding the dense layer for the output as a fully connected layers, and then we are making at the end soft max activation for the 10 classes. Okay, we have run that, and then we'll compile the model with the help of model.compile method, where we have a three important parameters. Optimizer we are taking Adam because it is very useful, and loss function we are taking categorical cross entropy, and then metrics we are taking the performance metric as accuracy, and we are printing that model.summary. See here in the model.summary you can say convolutional 2D you have output shape and parameter, how many parameters are taken, and in the max pooling how it has been downsampled, and how next convolution 2D has been taken, and next pulling 2, then convolutional 2D, then at last flatten, and then how dense fully connected layers taken the output shape, and at last as one of the 10 classes of images with the parameters 650. So total parameters are 1 2 2 5 70, and then trainable parameters like this and non-trainable parameters. So this is how summary we took, and then we have to train the model with the help of model.fit method with the xtrain, ytrain, and epoch says how many times it has to be run. 10 times we are making the epochs with a batch size 64, and validation data we are taking as a X test and Y test. So I have run already, and it is for each 10 of the epochs, it is making the training the model, and it is taking how many seconds and what is getting accuracy and loss function, validation accuracy and validation loss. So we have calculated and we got these all values, and at the last evaluating the model on test data. So with the help of test loss, test accuracy, with the help of the method model dot evaluate, it take the parameter x test and y test, and it found the test accuracy as 0.7103. It is 71%, it is almost good, and loss is 0.85. And at the end, in the step 8, we are plotting the training and validation accuracy with the matplotlib methods, taking the figure, plot, title, x and y label with a legend and a grid and show. It is showing training versus validation accuracy. Wherever there is a blue color, it is showing training accuracy, and validation accuracy, it is showing with orange color. So this is a number of epochs with number of accuracy. In the step 9, it is predicting and showing the sample outputs with a prediction of some X test. So taking the labels of prediction and true labels with the argument max with the NP, because numerical calculation of Y prediction and Y test. And here we are making the sample prediction with the range 2 or 5. We can take it as we like. And here I've taken two range, only two predictions. And I'm sure with X test of I and title, and we are showing it here. See, it's a blurred image almost, but it is recognizing this is a cat, predicting cat, and also true is cat. And next one is, say, this is a blurred one, but almost it is recognizing as a ship, and true is also a ship. I hope you got the things of how experiment we can do in the Google Colab. Let's come back to the our PPT. So, last key takeaway here, I can tell you that images can be classified using convolutional neural networks with the help of three layers: convolutional layers with ReLU activation function, and then pooling layers for downsampling, and fully connected layers for making the output with the help of softmax. And CNN has a filters as kernels to find the features map by multiplying input image matrix with a filter to extract the spatial features to classify images. So like this, we have a different successful CNNs to classify the images that also have shown it. Thank you.